Thank you. Yeah, it's good to be here indeed. I will not be talking on FMEAs, but I will be talking on, so what do you do afterwards when there's still probably some imperfection in your failure predictions. So I'm here from Eindhoven University of Technology, associate professor. So I've been here a lot before, not in this room, to be honest. So I studied at the University of Twente. So Jan and I actually shared an office for some time, so we know each other well. So Jan also explained me before that these FMEAs are not going well, and that was one of the triggers for me to go into this research. Another trigger was that at some point I was working with another high-tech company, not one of the suppliers of ASML and also not ASML itself. And the guy responsible there for logistic engineering, he told me that if he got numbers from the reliability engineers, so the NTBF, he first multiplied them by 10, and then he did his stuff. So that's how he, well, basically trusted the estimates from the reliability engineers. I'm not sure if his way of working was the best way to do it, but at least I noticed that indeed these predictions are not great, and then still afterwards you have to do something. So actually I was found for this symposium because of my most cited paper, which is on combining fault tree analysis and failure mode effect analysis with Johnny Peters, who now works at ASML. He didn't work at ASML at that time. He worked at Additive Industries, also here in Eindhoven. But my main focus in research is actually on predictive maintenance nowadays, so all kinds of maintenance optimization, spare parts inventory control. One of the things I'm especially interested in is using 3D printing in spare parts inventory control, but I don't think that will be very relevant for ASML in the near future. But it is relevant, for example, for the Royal Netherlands Army or for the Navy. And behavioral operations management, which is also somewhat related, because that is about, well, we come up with all kinds of algorithms and decision support systems. And then in very many cases, there's a human decision maker in the end. He gets some advice from the decision support system and may or may not deviate. And then in many cases, you see that people deviate. So yeah, then the question is, why do you develop a decision support system that's very advanced and then somebody deviates? So, right, so something needs to change. Maybe it's the decision support system, maybe it's the interaction with the human, it can be anything. But that's also a research interest of mine that is somewhat linked to today. So what I want to discuss today is three different topics. The first is a little bit on how can information be imperfect, and then how does that influence maintenance decision making, spare parts inventory control, and then I want to go into two specific examples. The one from maintenance optimization, that's a bit more, let's say, futuristic. I don't expect that we will implement something on this in the next few years. So I'll also go through that a bit faster. And then spare parts inventory control, that is somewhat closer to implementation. And that's work that we do with ASML. Okay, so first to this imperfect information. And let's say that if we would know for each part over the next few years when it will fail exactly, yeah, of course, then spare parts planning and maintenance optimization is relatively easy. It's not as straightforward as some people sometimes think, because, for example, let's say that my car, right, some cars now predict when something is going wrong. If I know that I have to go get some maintenance for my engine 4 weeks from now, and I also know that 6 weeks from now I have to do something with my tires, I can still wonder, do I go twice? Do I combine them? Well, if I combine them, it should be before 4 weeks, of course, and then, yeah, as close as possible to the 4 weeks. But you can imagine that if you have a very complicated machine, even if I would know exactly when everything will fail, there's still some thinking required. But okay, it would be relatively simple. What we often assume in spare parts inventory control is that there is that every part fails randomly. So we have some number, right? It fails every 5 years on average. And there's an exponential time to failure. So I assume that you know what it means, but it means that it is memoryless, right? So if I guess that it fails on average every 5 years, then even if I didn't see a failure for 3 years, my best guess now is again that it will fail, on average in 5 years from now. That's convenient modeling. It also means that I only need to receive one number from the reliability engineers. And if you have lots of machines together, you get a Poisson demand process, and you can use that for your spare parts inventory control. Right, so there is stochasticity, of course, right? This doesn't mean that every 5 years there's a failure. It's on average, and you can be unlucky at some point, but you can do the calculations. Since about 1960s, there are a lot of spare parts inventory models that make this assumption, and we are still in most of the models making this assumption, I think for various good reasons. Preventive maintenance, in this case makes no sense, right? Because with these assumptions, we have a constant failure rate. So it means that even though, let's say, that part didn't fail for 10 years, which would be highly unlikely up front, but the fact that it didn't fail for 10 years, under these assumptions, doesn't say anything about what will happen next. It is still as good as new, right? So preventive maintenance in this case would not make any sense. So we can complicate matters a little bit, go to some Weibull distribution. I think for reliability engineers, this should also be a common, well-known term. If beta is 1, we go back to that exponential distribution. But if beta is bigger than 1, and in the picture it's k, we get an increasing failure rate. So then it means that at some point, preventive maintenance does make sense. Spare parts models would still probably assume Poisson demand. And there's always lots of arguments about this, also internally when I discuss with my colleagues. The reason that in one of the earliest works was by Sherbrooke. What he already mentioned in his 1968 paper is that he gave the example, he worked with the military. If you have lots of airplanes flying missions, you have 100 or so. The fact that they all have some maybe Weibull distributed time to failure, as long as they are not all installed at the exact same time, which is highly unlikely, of course, they are phased in over some years. The overall process will probably be very similar still to a Poisson process. So for providing spare parts, it's probably still fine to consider this as a Poisson process and random failures. Of course, for your preventive maintenance, you should keep track of which aircraft did fly already and which did not fly that much. And of course, there are differences in failure modes and all the things you know. Nowadays, of course, we are trying more and more to go to predictive maintenance, which is this. Right, we monitor something. This is somewhat fancy with a drone going up in the air, looking at cracks in the blades, and then saying initially, well, there's only a 28% chance of failure over the next week or so, and then you see that going up. You also see that at some point it can go down, right? So here we thought that we were not doing great, and then we are doing somewhat better, but the overall trend is clearly it degrades. And the probability that it will fail soon is going up. Well, if we have this, that's very nice, of course, and we see the failure coming, and we can take action in time, both in terms of performing maintenance and also ensuring that the spare parts are there, but also the engineers, tooling, or in some cases have facilities ready, like the Netherlands Railways, right? They have to bring the train to some facility to do maintenance. So that's predictive maintenance. And of course, this is great if you think about remaining useful life and not wasting remaining useful life. But in fact, it makes maintenance and spare parts planning more difficult. And this is something that people not always realize. But if I have, let's say, if I don't do any preventive maintenance, so I just wait until something fails, and my fleet is sufficiently big, I have to admit that, then I will see something that looks like a Poisson process, and we have lots of models in place to ensure that we have spare parts available on average sufficiently. Right, so we can just decide up front, if we want to have a 99% fill rate, for example, we need to stock so many spare parts. If you do preventive maintenance, which is time-based, then I know already now that 1 year from now I will do maintenance again. So as long as you communicate that internally, which I also recognize, it doesn't always happen in companies, but as long as the people who plan the maintenance communicate with the people who need to plan the spare parts, it should be easy, right? I know that 1 year from now, I'm going to replace, for example, these blades. Okay, then I need 3 blades ready 3 years from now. Relatively simple. Then, of course, there may still be failures as well in between. So yeah, I also need to stock some well, in this case, blades. If some other failure would happen that I did not see coming, or that is not preventively replaced. But if I do this predictive maintenance, if I'm really monitoring, well, in theory, of course, if your predictive maintenance can predict a lot of time in advance that something is needed, you could still ensure that the parts and the people and the tools are there. In practice nowadays, in many cases, I have no idea about the blades to be honest, but in many cases that I've seen at companies such as ASML or Canon Production Printing or Van der Lande, they are possible to some extent to predict like 2 or 3 days in advance or so, sometimes a bit more, sometimes even less. Sometimes it's like 5 minutes, right? That really doesn't help me. The only thing is you can shut down your machine before the failure. That can be nice in some cases. But for my maintenance planning and spare parts planning, if I can predict, let's go to that extreme of 5 minutes. If I can predict 5 minutes in advance, yeah, then it's still a corrective visit. I still need to come after being called that something is wrong now. And if you tell me 2 days in advance, and it is a customer in the US, and I need to supply parts still from Veldhoven, then 2 days may also not be too helpful. Of course, I will probably have stock as well in the US. So with predictive maintenance, if you can only predict short time in advance, may actually be complicating maintenance and spare parts planning a lot. But still, of course, we are all trying to go in that direction. So what kind of imperfections can we have? Well, of course, we may not know the failure modes, as well in the extreme case of the black swans. We may not know the distribution of the time to failure, right? So even if at some point we can guess that it takes on average 5 years, but is that then some variable distribution and with what shape parameter, or is it really exponential distributed? And then if we don't know the shape, let alone that we know the values of the parameters. In predictive maintenance, in many cases, we may not know what to monitor. I've also worked on cases where we monitored something. There was a vibration in what was called the maintenance chamber, and they knew that vibration, if it came up, it could mean that either a filter was clogged, or some engine wasn't functioning anymore, and there was some third thing that could be the case. Right, so it can be in both directions. Sometimes you don't know what you need to monitor. In other cases, yeah, you know that there's something interesting to monitor, but even if you don't really know what it tells you, let alone how these conditions that you need to monitor change over time, and when they indicate imminent failure. Right, so in any case, you know that if something starts vibrating, that's not a good thing. But if it vibrates like this, is that really bad? I don't know. It can go up to this. Well, not in an ASML machine, I assume, but if you think about a Navy ship, maybe some vibration is not really a problem. So when does an increasing vibration really tell you that failure is coming soon? There are lots of things that you may not know. And I'll go into two of those examples. So the one is with maintenance optimization. This is ongoing research. Ragnar Eggertsson is the one who's doing most of this research. He's a PhD student in our group. And as you see, we work with the Netherlands Railways. So we work on the HVAC system, the heating, ventilation, and air conditioning. And in fact, we work mostly on the ventilation and the air conditioning. So it's about cooling and bringing fresh air into the car. There are 1 or 2 HVAC systems on every carriage. So you see them above the doors. I don't know if you see them, but they are above the doors. So at the end. And if they have too many failures in this system, then it leads to limited trains, right? Because if there are, I don't know the exact rules, but if there's one air conditioning failing, then it's still fine to run the train up to some outside temperature. But at some point, you can imagine if it's 30 degrees outside and the whole air conditioning system is not functioning, at some point they cannot run the trains anymore. This type of train then needs to go to Onne, because there they can replace the HVAC systems. And there are, I believe, 4, I don't know the English term, puts 4. So 4 tracks in the facility on which they can put the train so that they can go under and on top of it. Yeah, and that becomes then a bottleneck. So if you have too many failures, it leads to limited trains, especially, of course, in the summer. Problem here is that the degradation status is not known exactly. So they are measuring quite some things. But a lot actually of the maintenance actions are actually started because a conductor writes down that it was too warm in a carriage. So in many cases, well, it's now improving, but until, let's say, very recently, it wasn't noticed by some sensor. It was noticed by a conductor writing down it's warm in this train. There's probably something wrong with the air conditioning. They do have sensors as well, and they now measure the difference between the inside and the outside temperature and the differences in the one end of the carriage and the other end of the carriage, and then that tells them something as well. But there's really research still ongoing on that topic. What we have here, and this is the special situation here, is that failures are very obvious in the summer because then it becomes warm, right? It's also expensive in the summer in the sense that it really hurts your customers at that point. And if you have too many of these failures, you don't have enough trains, really bad for your customers. These same failures go largely unnoticed in fall, winter, and spring, because if it's cold outside, you will not notice that your cooling system doesn't function. So you can do some testing, right? That's of course what they do, but you will not see it automatically. They are also not that important in fall, winter, and spring because you don't need the cooling. It's different, by the way, for the ventilation, but for the cooling, this holds. So what this means is that both the costs and your observations are environment dependent, and the environment is then the season. And that's what we try to add to an existing model from 1986. I don't go into the model. I noticed actually in the previous slide that I could have added some mathematics and some difficult stuff in here, but I decided up front not to make it too difficult. What we see here is the environment states, and this represents the winter, spring, summer, and fall. And what you see come out here now is that you get maintenance policies that depend on the environment. So it means that in the middle of the winter, we only inspect if we are pretty sure that something is wrong. So what you see on the left, on the y-axis, is it's related to how sure we are that the failure is upcoming. And if we are very sure, then we will inspect to be completely sure and then do maintenance. But if we think there is still a good chance that there's not a failure upcoming in that system, we just continue because we don't really need it in the winter anyway. Then you also see that in spring we do a bit more of inspections than in fall. Because in spring you already want to prepare for the summer. And in fact, what I think we need, something is still missing in this model, I think. Because what I expect is that you should do much more inspections in spring actually to really prepare for the summer. At the same time, we also notice that in many cases the problem is that a failure is a new failure can come up very quickly. So ensure you should do inspections in spring and fix what's wrong already. But if you have another 3 months to go, if something is upcoming, there's a high chance you won't see it coming. And and lots of inspections, of course, in the summer. So there, if you think, well, something is going wrong, potentially inspect it and fix it if needed. Now, here is at least a lot of numbers to make it a bit complicated. What do we show here? If you take into account that there is this difference in time, so that in some seasons you know more, but also your costs are different. If you take that into account, that's what we do in that optimal policy. And you compare that with this, oh yeah, that doesn't work, the aggregate policy. The aggregate policy does a good maintenance job, but ignores that there's a difference between the seasons. You see that that aggregate policy, well, in the base case, has 12% higher costs. So what does that show? That shows to me that that even though you have inaccurate information, the fact that you take into account that whatever you know in the right way can save a lot of money. And you see that in some other cases it can go up to 20%. You also see that in some cases it doesn't really matter. And I don't think at the moment we can say to the Netherlands Railways in which cases it wouldn't matter and in which cases it would matter, which of course would be an interesting answer for them. What we see here is that in the base case, it's the same base case I think as on the previous slide. We don't have that perfect information in any case, right? We have different information over the different seasons, but it's never perfect. What we do here is with the sigma 1, 2, 3, and omega 1, 2, 3, and 4, is if in one of the seasons we would have perfect information, only that one, how would that influence our cost? And then you see that if we would, I think you would have expected this, if it is in summer that we have perfect information, then that reduces the cost the most. I think that's obvious, but it's of course also nice to see here is that perfect information in spring is more worthwhile than in fall, for the reasons that we already discussed. And if you would have perfect information in all cases, in all seasons, it would reduce costs a lot. So these are the kind of things to explain probability to management, like maybe invest a little bit more in figuring out how this failure behavior works and making those predictions better, because you can actually save a lot of money. Okay, so it does show we can do something even if there's very limited information with predictive maintenance. There's still a lot to do, so indeed here we end with what don't we know. Yeah, those algorithms are very slow, so we really need to make it faster. Now we work for one component with 4 seasons, and it already takes a day to solve or so. If you would have all the components in a train and you would consider that even the months are different, yeah, we are really not capable of doing that. So for any practical value, this is not there yet. Of course, we don't need to start with complete trains. We can start with the key systems or the key components. So I think we can do something in some years, but not. I don't think this will be implemented next year. Okay, then let's go to this spare parts inventory control. That's different. Well, ASML. So here the PhD student is Zhao Kang. Somewhat bigger team here. And what's nice here is that Johan Stip is involved, and Johan Stip works here at ASML, is responsible well for part of the spare parts inventory control. But at the same time, he's now doing PhD studies. So he's also into the research, but he really knows how everything works in detail. And of course, we try to understand that as well. But if you are at the university, you never have the knowledge, of course, of the company that somebody at the company has. So I'm really happy that Johan is on board as well. And it's about robust spare parts inventory control. Here we really started with the idea that, especially for new product introductions, you don't really know what kind of demand rate to expect for your spare parts. Right, so there are some estimates, there are some FMEAs, there are some estimates of mean time between failures, and you know how much equipment you will have in the field at some time and in which area. but it's very hard to estimate the demand rate. Historical demand rate data is very limited. I think Jan mentioned, right, in many cases there's some machine that looks a bit like it, or key parts of the machine look at least like key parts of some other machine. So you have something, but it's limited. And then there's this problem that demand is very intermittent. So that is what you see here on the right. This is the demand that we have seen for 2 different stock keeping units. And then you see that there are months where nothing is demanded, and then 4 are demanded. And here at some point, this is probably something strange going on, like maybe they did an upgrade. So this probably shouldn't be in this data. But yeah, if the upgrade is not communicated up front, then it will be in the data. But this is very common to see that there are months without any demand, and then there are months where you have to deliver 4, and then the month afterwards again 4. And if you're stocking spare parts and you think, well, no demand, no demand, no demand, yeah, and then you have 4 to deliver, or even worse, you have 4 to deliver and it takes you 2 months to get new parts, and the next month again you have to deliver 4. So this is very typical, right? If you look at the different parts and the different stock keeping units, there are some parts that fill relatively often. For me, that's nice. I can do my math. Typically, of course, this end you get upgrades and redesigns. So then, even after the redesign again, I have no idea about the failure behavior and how much to stock. But there's always also this long tail, which I think, yeah, it is apparently designed right in the sense that it doesn't fail that often, but then to stock parts is quite difficult. Same time, you want to have a high service target, right? Because your customers are not very happy if you tell them, I don't have that part on stock. Even more so if that part is not too expensive in the end. I think you can probably correct me if I'm wrong, but I heard the number of 72,000 euros for an hour of downtime at a fab of a customer. So if you then tell them this part of 10,000 euros, well, yeah, I don't have it. Yeah, your customer won't be happy. So you need a high service target, but yeah, there's also this problem that you have it's very hard to estimate this initial demand rate. So you can stock more to be sure. Excellent for your service performance. If you stock less, yeah, that's poor service. High investment cost, of course, is the key drawback of stocking a lot. It does mean that there are not too many penalty costs. You have happy customers. But there's also more inefficient stock. Right? So this is, I think this is the ASML definition, that stock is called inefficient if it has not been used for 5 years. It doesn't, of course, necessarily mean that it will not be used afterwards, if you talk about this long tail of spare parts. But in general, you want to prevent having too many parts that are part of this inefficient stock. So this is difficult. So you want to have something that's robust and at the same time cost efficient. So we started working on this. For now we model that we have one warehouse, but with emergency shipment. So this would be one local warehouse in Taiwan, for example. I'm not sure if I think there are 3 local warehouses in Taiwan, so maybe you should combine them. But we model one, but there is some emergency shipment possible. So if we don't have the part on stock, there is some way to get it relatively quickly from somewhere else. Could be from South Korea or Singapore, but could also be from, well, Veldhoven if needed. We consider that there are multiple critical components that we need to stock there, and we assume a base stock policy. So we're looking at not too cheap items. If you have really cheap items of 100 euros, yeah, you will not replenish them one by one. So I'm thinking here about items that you replenish one by one. I don't know what the minimum cost would be at ASML, but let's say items of a few thousand euros are probably already in that category. And this is also a very common assumption in those spare parts model, that we look at more expensive components and we assume that every time you use one, you immediately send it to a repair shop or you immediately order a new one, depending on whether it's repairable or not. So we get this system in principle. There's demand to the warehouse. If the part breaks down, it goes to the repair shop and it gets back as a repaired part. If you cannot repair it, and then it goes away, but you still get a new part. So it doesn't really matter if a part is repairable or not for this model. Then there's a true problem in practice, right? There's all kinds of information that we have for stock keeping units. And we have historical demand data. Or at the least we have an estimate, the reliability estimate received from reliability engineers. So probably one number that says mean time between failure is 3 years for one component. What do we do here? We use part of the set to train. And then two things, this is important to understand. We either fit this Basten process or we fit an uncertainty set. And the Basten process is what I explained before. That is what is typically used in those spare parts models. So we basically use a conventional spare parts model there. The other thing is the uncertainty set. That is a term that comes from robust optimization. And it means that you basically create a set of all the possibilities that could arise given the information that you have. So if you have historical data, you basically have the set of all the historical points, and you probably take a bit of more space because, well, if this can happen, then probably a bit worse can also happen. But you need to construct that uncertainty sets, and there are various ways to do that that I won't discuss here now. But that's the key difference. We either use that conventional spare parts model or this uncertainty set for a robust optimization model. Both of them, we let them give a solution, basically giving a number of spare parts to stock for each type of component in that one warehouse. And then we test with the test set, well, how do they perform? What we then use in the simulation study, so we are still going to use this with ASML data, but as I told you, we have Johan on board. Zhao is at ASML, I think, every Friday or so. So I'm sure that we will get the good set to really test this. But for now, we did a simulation study. We only used this. So the actual demand we generate with a gamma distribution or a Weibull distribution. We have a mean. That's the number that both of the models get. They don't know if it's gamma or Weibull or something else. And in the one model, as explained, we assume it's Basten distributed, so it would mean exponential. But we have the mean. That is given, and then we vary. So the k is varied here, and then you see that the mean is going up or down. So in the simulation, we just vary. The actual demand turns out to be different from what we expected. So the mean was 2.5, that's what we based our model on, but it turns out to be 4. And then we see how the two models work or function. And what you then see happening here is at the top, you see the total cost. Left is the gamma, right is Weibull. I think the results are very similar. And at the bottom, you see the fill rate. And the fill rate is the number of demands that you can fulfill immediately. So demand comes in, I have something on stock for that demand, it's fulfilled. Or I don't have it on stock, and then I have that emergency shipment. So the percentage of time that I had the component on stock when I needed it, that's the fill rate. So higher fill rate is better, lower cost is better, right? What we see happening here is that we thought it would be 1, that's what was given to the model. And if it is actually 1, you see that the blue line, that is that greedy approach, the conventional spare parts model, it does a better job than what we now propose, the robust optimization. And that makes sense, because that model, well, first of all, people have worked for it for 60 years. But that model also is built on the fact that it will be that demand rate. So yeah, of course, it functions well. In the robust optimization, we had that uncertainty set, so we didn't tell the model it will be that, it will be something in this area. And it basically gives a solution that performs still well in the worst case. So what you see happening here is that if the demand turns out to be, and I have to say this right, much higher, then the fill rate with the robust optimization still remains okay. 90%, not great, but okay. I think our target was 95%. You see that conventional model, it really fails. And at that point, you see that the conventional model does a good job. If you look at the total cost, you also see that the greedy, so the conventional model, the total costs remain smaller over quite a wide range, but if it becomes more extreme, you see that your costs go out of control. And you see that in both cases. So what this means is that what we're now thinking of is that in that case study, we want to first look into if we have a new product introduction, so we have only the estimates. If we then go, so a new product introduction of 3 or 5 years ago, we take the data from the last 3 or 5 years and we let both algorithms stock inventory. And then we want to compare, did it do well? Did the robust optimization give better solutions in terms of a more stable fill rate with not too much additional costs? And then at some point you probably need to go to the conventional models, because if the product has been in place for 5 years or so, then you probably have enough information on the demand rates that you can use the conventional models. So next question would be, when do you have to go from the one system to the other? But again, it shows that, as long as if we know, let's say, the uncertainty that is there in the predictions, we can do quite well in spare parts inventory control, just as we did in maintenance optimization. It would be important, of course, that people don't just get a mean time between failure, but something more than that, I guess, in line with what Jan was explaining. Also here, still some improvements to make, some more simulations to do, but we are actually starting very soon on that actual case study. And then if this turns out to work, then history teaches us that at ASML we have been able to implement spare parts inventory control models before. So I wouldn't be surprised if the case study is successful that we can really get this implemented, well, maybe not next year, but then at least a year afterwards. So that's it. I hope that I remembered you that, if reliability engineering, failure modes, effect analysis, if everything's perfect, then after sales service delivery is easy. If it's imperfect, which I expect to be the case for the next few years at the least, then still we can do a lot. It does help really if we know how imperfect the estimations are. And I hope that I've given you some ideas of what's possible. And if you're working in this, we're always looking for interesting data sets to learn more, improve algorithms, apply, see if they really work. So you can always feel free to contact me for questions or if you have interesting problems in this area. And then I think it's time for questions.
Well, first, let's give them an applause. I already saw someone with a, here.
Yes, something about the changing environment. And we also see you can still have a perfect FMEA up front and perfect predictions, but still we cannot look into the future like changing environments and climate change. It's also affecting our equipment. So are there any developments in that direction? Or? If you understand what I mean, changing environments will affect also the performance of a system, or just in the cloud for airplanes, for example.
Right. But I think the question is then more about the FMEA side, right? Of how do you improve your predictions?
Yeah, that's fair to say. You can still have a perfect prediction and everything would be easy, but you see a lot of changes.
Yeah, okay, yeah.
Perhaps one thing to say there, you have to be sensitive for failure as an organization. So often people, if they see something going wrong and they think, oh, that is not my specific area, let Rob do that stuff and I will keep my own. And I think what's important with these complexities is that you also see that you have an atmosphere, a culture, even if you're not sure that things go wrong, that you're already sensitive to look up ahead and find out and see, for example, there is a trend coming up. Can this impact us? Yes or no? And that you have a kind of expert discussions on this kind of things. But I am in a lot of companies that they say you should only do testing and then have good project management with prints and then everything is there. So the black swans, I really appreciate that presentation. That's really true. But we have just to accept that they are there and have to handle from there. So just accept that it is there and also try to bring up a culture to be open to work on this. It's like if you're in a hospital and someone is in a room and has a problem and a physician is passing by, then the physician will just look and try to find the answer. But that's the culture. People want to help and try to put their energy in it. I think in ASML that's also happening a lot of times, but you have to energize that feeling and also be open for just things you didn't know. Don't blame each other, but try to work on it. But it's really difficult in practice. So you need to nurture a culture to do this kind of things.
If we go back to the spare parts, I think what you see in some companies is that, well, it's also about continuous improvement, right? So some companies you see that they set the spare parts levels, and then there are people operationally responsible for the spare parts inventory control. They deviate a lot because they have knowledge, but they don't change the levels or the technical levels in the system. And I think so other companies, and I think ASML is one of the examples, but there are many more. Every 3 months or so, they have a good look at the technical levels and they adjust the levels. So then you're not just every day covering for the additional dust in the air, but at some point you just realize that all your stock levels have to go up because there is more dust. And I think that loop of going back to your data, updating your forecast, that has to be there. And I think it is improving, but there are still companies and organizations where that doesn't really happen.
Other questions?
I was just thinking about with the fill rate, did you look at the fill rate only of ASML because ASML doesn't produce the parts? So isn't it the fill rate of the entire supply chain that's going to be the actual fill rate there?
So the fill rate for me, the fill rate or the fill rate? Fill. Okay. Now, so the fill rate for me is really, I have that warehouse in what did I say? Taiwan. And can it deliver that part at the moment it's asked? So is it in that warehouse at the moment that it is needed? And then, how does it come that it is not there? That's another question indeed. And that's something that we do look into. I think in the conventional models, you typically just assume there is some lead time, which can be very long. That's fine for the calculations, but we just assume it's there. It may have a distribution, that's fine. There is also research on disruptions. And there's also research, for example, on predicting when, well, it's actually some of the things that we are also now working on, predicting when your supplier may take more time than in the past, or maybe even predicting that a supplier at some point stops delivering. Right, it also happens that your supplier just at some point tells you, well, that part is not there anymore, so good luck.
Yeah, so I'm asking also because we've done some research on that as well with regards to which parts of our million parts are we going to 3D print for this intermittent or radical change, crazy demand.
Right.
And what we've seen there is also that demand for us might show up as periodical because you order according to a base stock strategy, when in fact it's actually a whole different demand pattern which we could anticipate on. So it would be very interesting to look one step behind and also look at how you could fill it, especially with long lead times like 3 months. Our fill rate might be low, but in fact the whole chain might have survived it.
Right.
I think that's a perfect discussion to continue during lunch.